So in this video, what we're going to do is state the induction and recursion theorems for ordinals, right? Ordinals are well-orderings, and so, well, we prove some type of induction on a well-ordered set and recursion on well-ordered sets. That means that we can kind of translate those results into the setting that we're currently thinking about with ordinals. So maybe what we'll first start with is induction. So I'm going to call it, here's maybe our theorem, and this would be ordinal induction. Ordinal induction. And there's one subtle difference between this statement and the statement that we proved for induction on a normal well-ordered set. And so what is the statement? Well, suppose that we have some property p of x. Suppose we have some property p of x. And what we want to prove, what's our goal, is we want to show that this statement is true for all ordinals. And so suppose that we have this, and suppose that we can prove, and for each ordinal beta, well, we have the following statement. The following is true. What is this statement? It's, well, if it's true for all ordinals less than beta, so assume that this statement is true for all ordinals less than beta, well, then we can actually argue that it's true for beta. So this is our kind of star statement. Let's just suppose that we could prove this. Well, then p of x is actually true for all ordinals. So then for every single beta, p of beta holds. So in other words, for every ordinal beta, maybe you should make clear that's an ordinal, for every ordinal beta, p of beta is true. What is this kind of one difference between this and the normal induction? Well, we proved already that there's actually no set of all ordinals. And so what this is doing is that this statement is going to be true for all of the ordinals, and which kind of, so this would be true for some proper class of stuff. And so we can't just immediately appeal to the induction theorem that we've proven already, because, well, that was when we were only dealing with sets. We wanted to show that was something. We wanted to show in that case that something was true for all elements of a set. And well, this is something a little bit bigger. There are more things. There are more ordinals than they don't form one set. So how do we deal with this? It's just a little trick. What's the proof? Well, if we want to show that something is true for beta, what we can do, so what is our goal? We want to prove, well, for every beta, that p of beta is true. So we could say fix beta. That's some ordinal. And sometimes what's happened, sometimes the way that we denote this, instead of writing is an ordinal, I don't know if I've written it so far, but what we can write is, well, is an element of ord. Sometimes this ord is to denote the collection of all the ordinals. And again, it's not a set. It's a proper class. But the collection of all the ordinals, we could just say, well, beta is an ordinal, is how we'd read this. So we can fix on beta. And well, how do we appeal to the induction, the kind of induction result that we've proven already? Well, we need to kind of deal with sets that are well orderings. And so what we can do is apply the induction result, induction theorem, to what ordinal? Well, to beta plus 1. And again, emphasizing that this is bigger than beta. So in other words, beta is an element of beta plus 1. And beta plus 1 is a well-ordering. And so what we could do is apply this ordinal induction, or this induction on well-ordered sets, to the set beta plus 1. Well, that would allow us to conclude that for every alpha, say, in beta plus 1, p of alpha is true. But, well, beta is an element of beta plus 1. And so we'd get p of beta to hold as well. And another thing I'll mention, I don't know if I've done this already, but there's a name that we use for kind of ordinal induction. Sometimes it's called transfinite induction. So this is sometimes called transfinite induction. This is called transfinite induction. transfinite induction. Okay. All right, so this is going to be an extremely useful tool for us later, but this is the statement for induction when we're dealing just with ordinals. And we want to show that some property is true for all ordinals. Okay, so what's the other the other theorem? The other theorem was involving recursion on well-ordered sets. So we're going to have some similar statement for defining some recursive sequence on an ordinal. So actually, maybe one thing I want to add with this induction results, is that how do we end up normally proving this star, right? At the end of the day, if we want to use induction, we need to prove this statement star. So how do we prove this? So note, in practice, proving star amounts to breaking up our argument into 3 cases. So amounts to checking amounts to well, what am I trying to say? Well, we want to prove that star is true. Well, we want to show that this is true for all beta. What we normally do is we consider the different cases that beta could be. Beta could either be 0, or it could be a successor ordinal, or it could be a limit ordinal. So in practice, proving star amounts to considering the cases where the first case would be, well, beta is equal to 0. The second case would be, say, beta is equal to alpha plus 1 for some alpha. And then the third case would be that beta is a limit ordinal. So that's in a lot of ways, in a lot of situations, that's how we'd end up proving. That's generally how the induction goes. Okay, but how do we do recursion on ordinals? So the theorem. What's this theorem? This theorem is ordinal recursion. And so what's the result? So this theorem is going to be kind of, again, I'm going to state the one that we've proven already. It would be something like this. So fix some ordinal beta, or some ordinal theta. So fix some ordinal theta and some function. Maybe it was f, which was a function. In this case, it would be from theta times p into b. Now, what were these things? B was some set, and p was the set of all partial functions from theta into b. And what f is supposed to do is tell you what the rule is to kind of generate the next element of your recursive sequence. So where b is a set, and p is all partial functions. The set of all partial functions from, well, theta into b. Well, what was the result of our kind of recursion theorem is, well, then there is some unique function g. So there's a unique function g, which is a function, in this case, it's going to be from theta into b. Well, such that what? Well, it would be such that, well, for every single, say, alpha less than, theta. Well, what would g of theta be? Or sorry, g of alpha, what would that be equal to? Well, that should be the alpha thing in our kind of recursive sequence. Well, that's going to be what the rule tells us to do when we have access to alpha and all the previously defined values. And the way that we can denote this, which I think is which I always thought was kind of cool, is that we could denote this as, well, g restricted to alpha. So before, just as a note, before, what did we put right here? Well, this would have been something like the set of all, like maybe z in A such that z is less than less than like A or something, right? If we wanted to figure out what G of A was. But, well, we're thinking about theta as theta is a well ordering. What's our less than? What's our well ordering? It's the epsilon relation. So this thing is just Z is an element of A. In this case, it's Z is an element of alpha. Well, what is that? That is just alpha. So these two things end up corresponding with each other for ordinals, which I thought was kind of cool, which I think is kind of cool. Okay, so this is what the recursion is saying in this context. Again, just something I maybe mentioned. This is something I mentioned in the proof of the proof of the recursion theorem when we did it a few videos ago. But I don't know. I think it's good to maybe just say it again. Given the statement, we're required to say what B is in advance before we do the recursion. And this isn't an issue when we have when we maybe are defining a bunch of natural numbers or real numbers or something like this, where we know what the set is that our kind of recursive outputs are going to be. But sometimes what's going to happen, and our next example will be something like this, maybe, where we don't know in advance maybe what the set B is going to be. So how do we deal with this? There are different versions of the recursion theorem that allow us to kind of maybe not state B directly. But intuitively what's happening is that, well, at each stage what's happening is the proof of this went by constructing a bunch of approximations. So maybe our first thing that we figured out was what would be G of 0. We figured out what that thing is. And then what we figured out was what G of 0 and then G of 1 was. Maybe I'll write them not with curly brackets, but with kind of emphasize that it's a sequence. We're defining a function. So, and there's maybe G0, G1, and then G0, G1, G2. Whoops, I wrote that again. G2. And it keeps on going. So in the proof, we kind of proved that we could construct all these approximations of our function G, and then what we ended up doing was taking the union, and it all worked out. Well, what we could do, maybe if we don't know what B is we could prove in all of these stages that, well, we can keep track of what the I guess the codomains or the output spaces are for all these approximations, and then we can kind of union those all together to figure out what our B would have to be. So I'm just saying that, again, just it's more of a technical point. Maybe I'm kind of saying too much about it, but maybe there's some issues with explicitly saying what this is. But a lot of times, if we're going to give some recursion, we're not going to state it. We're just going to describe what the process is to generate the new element in our recursive sequence, and then appeal to the recursion theorem to say that we can do something like that. Okay. Oh, I guess one more point too is that this was defined on an ordinal, right? We're fixing an ordinal, and then, well, this function, well, it's a function and it's defined for all ordinals less than, say, theta in this case. Well, what we can also do is sometimes this rule that we're doing to kind of construct a new element of our recursive sequence, sometimes this actually doesn't depend on theta at all. And so what happens in situations like that is, well, you end up defining some type of element for all ordinals. So maybe another note. If our rule F doesn't depend on theta, well, then what happens is we can think about our recursion as actually generating a whole proper class, or maybe not it's a proper class, but our rule is actually defining a whole collection of sets for every ordinal. So then we can think about, then we can imagine that our maybe say that we are constructing a sequence, maybe a recursive sequence. recursive sequence. Maybe it's A sub alpha, where alpha is what? Alpha is going to be some ordinal, right? This technically isn't a function, right, or a sequence, because, well, this is the domain of this function would be a proper class, right? The ordinals isn't a set. But we can kind of think about our rule as, well, we could have kept on going if we wanted to. And we're stopping maybe at some point theta, but that might just be arbitrary. And so if we're doing some recursion and we don't specify like what this domain is, well, it's just implied that there's some maybe really big ordinal in the background that we're kind of fixing to do this particular recursion. And again, this is another one of these types of results where when you do more advanced kind of work in set theory, they have other statements that allow you to do these types of recursions where you get a new, where you kind of make more formal the ability to do a recursion on, say, a proper class of a set that's a proper class instead of, or sorry, not a set that's a proper class, a proper class instead of a set. Okay. All right. So again, maybe I'm kind of going too much into the weeds. All right, let's do an example, and we'll talk more about this in the next video. But let's give an example of, this is called the cumulative hierarchy. The cumulative hierarchy. So this is the cumulative hierarchy of sets. Well, what is this going to be? Well, I guess what we're doing in the background is we're fixing some large ordinal. So fix some large ordinal theta. And what we're going to do is define a collection of sets for all alpha less than theta. So define. So for all, I'll kind of, so I'll say something like this. So for all alpha less than theta, define the following. So the way that we're going to note this, it's going to be denoted V alpha. V alpha is supposed to represent the stage of the cumulative hierarchy. Like it's a stage of the cumulative hierarchy. So what is it? As follows. Maybe I will. I'm going to put this in parentheses because just kind of going off of our previous conversation, this definition won't depend, or this recursion won't depend on theta. And so we can think about this as really just being defined for all ordinals, where we just kind of fix a large ordinal in the background. So what is the definition? I need to tell you what we need to do when alpha is 0. So if alpha is 0, what we're going to do is define V0 or V alpha. That's just going to be defined as the empty set. Well, the next stage is I need to tell you what we need to do if alpha is the successor of something. That's the next type of ordinal. And what's going to happen here is, well, V alpha is going to be defined as the power set of the previous thing that we've defined. So in other words, another way to write this is that V beta plus 1 is equal to the power set of V beta. And then, well, the last situation is, well, what if alpha is a limit? What if alpha is a limit? What we're going to do is we're going to take the union of all the stuff that we've done before. So V alpha is going to be equal to the union of maybe all of the beta less than alpha, such that, well, of V beta, right? So if we've defined all of the V betas up to alpha, what we're going to do is take the union to get the next element in the next stage in our cumulative hierarchy. All right, so this is the recursive construction, or the recursive definition of the cumulative hierarchy of sets. If we wanted to be a little bit more formal, maybe what we could do is say, so maybe more formally, what we're kind of doing if we want to kind of have it closer, if we want to make this thing look a bit closer to this statement of recursion, well, we're going to have some function f from theta times p into what? Well, this is just going to be some set that's going to exist. So it'll be some big set. And this set, I guess we'd argue, exists by replacement. So which exists by replacement. maybe I'll write it like this. Big set. And this set is going to exist by replacement. And then what is going to be the, what is this function going to do? Well, the first thing would be, well, if we have maybe some input alpha and some partial function g, well, the output of our rule is going to be by cases. It's going to depend on what these values are. The first one is, well, if alpha is 0, we're just going to output the empty set. So if alpha is 0, we just output the empty set. Well, the next situation is, well, let's assume that alpha was the successor of something. So, and well, what did we do in this case? Well, we took the power set of the previous lead defined value. So in this case, well, if alpha is the successor of something, what we're going to output is the power set of the previously defined value. What is the previously defined value in this kind of more formal setup? Well, that's exactly coded by this partial function g. Well, the previously defined value would be beta. So this is if alpha is equal to beta plus 1. So in other words, if alpha was the successor, well, and I guess g could be any partial function, so we want to assume that beta is actually in the domain. So and beta is in the domain of our function g. So in other words, if we are in the situation where alpha ends up being a successor, and we have some partial function where the previous this beta is in the domain of our partial function, well, we're going to take the power set of what the output of g is when we kind of input beta. So again, g is representing like all the previously defined values. And then this last situation is, what if alpha is limit? What if alpha is a limit ordinal? Where, well, what did we do? We took the union of all the previously defined values. We can think about that then as the union of all the previously defined values. What's that going to be? That's going to be all the set of all the g beta, such that beta is less than alpha. And well, there are two kind of conditions that we need to happen that need to happen here. Well, alpha needs to be a limit. So if alpha is a limit ordinal, and this other situation is, well, g beta should be defined for all values of beta, for all values of beta less than alpha. So another way of expressing this is that alpha needs to be a subset of the domain of g. And I guess there's one final thing. So what if none of these conditions hold? So I think the way that we did this when we defined the Fibonacci numbers was we included some additional additional set that we called error, and maybe we can do the same thing. So we can say error otherwise. Okay, and so what's happening here is if you kind of work through what is supposed to happen, what you're going to get is exactly this cumulative hierarchy of sets. So in other words, well, what is g of 0 going to be? Or sorry, well, g of 0 would be, g would be the function that I guess in the recursion, but yeah, so maybe we'll write it like this. So what would g of 0 be? Well, that's going to be what? That's going to be f when, well, we have 0 and all of the stuff before it. But there's nothing before it, so this is, I guess, just the empty set. Well, what is this output going to be? Well, this is just the empty set, right? Because, well, alpha is equal to 0. It doesn't matter what this partial function is, so we're just going to output the empty set. Well, this corresponds exactly with what v0 is equal to, right? v0 is this piece right here. And then, well, what should v1 be? So g of 1. And I'll call this, maybe I'll write it over here. This will be v1, and then this is v0. g1 is going to be what? This is going to be f of 1 when we have access to all the previously defined values. So what is this thing? We can think about this. This is the function, or this is the sequence, just g0. Right? That's what kind of this piece is. This is a function whose domain is just 0, and whose output, so the output here, is the empty set, right? Because that's what v0 is. And well, what is this going to be equal to? Well, alpha is the successor of something. It's the successor of 0, and 0 is in the domain of this function. So this is going to be the power set of g0. which is the power set of V0, well, that matches up perfectly with what we should have gotten up here. We've taken the successor, or we've taken the power set of the previous stuff. And this kind of keeps on going on. So it'll keep on going on like this. Okay, so what we'll do next time, so in the next video, we'll kind of recap this definition again, and we'll go into actually proving some theorems about the cumulative hierarchy of sets.